In this video, we're looking at a classic buoyancy problem involving a hot air balloon. So we're given the total mass of the balloon material, the basket, the passengers, the equipment. We're told that's 500 kilograms. We're given the density of the cold outside air as 1.24 kilograms per cubic meter, and the density of the hot air inside the balloon as 0.95 kilograms per cubic meter. In part A, we're going to compute the volume of hot air required to lift this balloon. And we're making an approximation in part A. We're ignoring the buoyant force on the passengers and equipment. So the passengers and equipment, they're displacing a certain amount of the surrounding air. That should generate a small buoyant force, but it turns out to be a very small percentage compared to the buoyant force exerted on the balloon itself. In part B, we're going to relax that assumption and get a slightly more precise answer to the question. One extremely important point about this problem is that we can't ignore the mass of the hot air itself. That is part of the balloon system. Gravity pulls down on that hot air, and it actually turns out to be the majority of the weight of the balloon system. And one more note before we get started. Recall that density has the definition mass per volume, mass per unit volume. If we turn that around to solve for mass, we get mass is density times volume. And that's a little calculation we're going to use repeatedly in the solution of this problem. It's just nice to be prepared to do that quickly. So to start out the physics of the solution here, we'll put in our force vectors. And that downward force vector, that's the force of gravity on all the mass contained in the balloon system, including all the equipment and passengers and the air inside the balloon. And I'll just call that mg for now. We'll split that up into a couple smaller parts. The upward force, that's the buoyant force on the balloon. And remember, Archimedes' principle says that's going to be equal to the weight of the displaced fluid. In other words, the weight of the cold outer air that's been pushed out of the way by the volume in this balloon. So the basic physics of the problem starts out by saying, if we're going to get this thing to float, these forces should balance each other, and the buoyant force will be equal to the total weight. But then we have to get into the details of each of these two forces. We'll start with the buoyant force. Again, that's going to be equal to the weight of displaced fluid. In other words, what's the weight of all the cold air pushed out of the way by the volume of this balloon? Well, that's going to be the mass of the cold air pushed out of the way multiplied by g. And the mass of the cold air pushed out of the way, again, we use this density formula solved for mass very frequently. The mass of that cold air is going to be its density, so I'll write it as rho cold, times the volume of cold air pushed out of the way. I'm going to call that V, that's the volume of the balloon, times G. Okay, so those are the details of the left side of our equation. On the right side, we had mg, where m is the total mass of the entire balloon system, including all the equipment, passengers, and balloon material, and so on, and the mass of the hot air inside of it. So that little m is the mass of the equipment. I'll call it MEQ, that was 500 kilograms, that's given to us, plus the mass of the hot air. And the mass of that hot air, again, is given by the density of the hot air multiplied by the volume of the hot air, which, again, we're using a capital V for the volume of the balloon. Okay, so then we plug in these details back into our original force equation. And this is our buoyant force. It's the density of the cold air times the volume of the balloon times G. And then on the right-hand side, the total mass is going to be M for the equipment, plus the density of the hot air times the volume of the balloon, all multiplied by G. Now the G's cancel out of this. And I noticed there's two places where the unknown volume of the balloon occurs. Once over here on the left-hand side where it was involved in the calculation of buoyant force, once over here on the right-hand side where it was involved in the calculation of the mass of the hot air. So we subtract that term on the right-hand side, moving it over to the left, and we'll factor a V out on the left. This leaves me with rho cold, the density of the cold air, minus rho hot, the density of the hot air, multiplied by V. And on the right-hand side, we're left with M for the equipment. And we'll go ahead and solve symbolically for this volume. Before we plug numbers in, I get mass of the equipment divided by the cold air density minus hot air density. And now we can plug numbers in, and we get 500 kilograms, the given mass of the equipment, divided by 1.24 kilograms per cubic meter, the density of the cold air, minus 0.95 kilograms per cubic meter, the density of the hot air. And when we run the numbers on this, we get about 1,724 cubic meters for the volume of the balloon. Now, before we move on to part B, I wanted to reiterate how important it was for us to include the mass of the hot air itself. Let's go ahead and calculate how much that was. So the mass of the hot air, again, just using this density formula turned around, is going to be the density of the hot air times the volume of the hot air. So that's 0.95 kilograms per cubic meter for the density, multiplied by this 1,724 cubic meter volume for the balloon. And this turns out to be about 1,640 kilograms. It's actually the majority of the mass, far more than the actual equipment. So let's improve on our answer by including the buoyant force on the passengers and equipment themselves. So we were given a total mass there of 500 kilograms. Now we're given the average density of all the people and equipment as 1,500 kilograms per cubic meter. Well, to find the buoyant force caused by these people and equipment simply being immersed in cold air, we need to get their total volume first. And this time we have the mass of all that stuff and the density, which allows us to get the volume. So I'm going to write down just a reminder of the definition of density, mass per unit volume, which means if you solve for volume, you get mass over density. So we're going to call this VEQ for the volume of the equipment and people and so on. And I get 500 kilograms over a mean density of 1,500 kilograms per cubic meter. And this gives me exactly 1/3, or we can write down as a decimal about 0.333 cubic meters of volume. So to get the buoyant force generated by this 0.333 cubic meters of volume, we need the mass of the cold air pushed out of the way by the equipment and people. So I'm going to call this contribution to buoyant force. I'll call it FBEQ. And that's the mass of the cold air pushed out of the way. So it's going to be the density of the cold air times the volume of the equipment and people times G. Then we get back into the same type of force analysis, but this time we realize that our total buoyant force has two different contributions. There's the main buoyant force on the balloon itself. I'll just call that FB. And then there's also FBEQ, the small additional buoyant force on the equipment itself. And of course, pointed down here is the total force of gravity, that's mg. So to get the balloon to float, we balance the forces. And then we start putting in the details. The buoyant force on the balloon itself, again, is going to be the density of the cold air times volume of the balloon times g. That's the weight of the displaced cold air, plus our additional small buoyant force on the equipment and passengers themselves. Again, they're pushing cold air out of the way, so density of the cold air times VEQ, the volume of the equipment, times G. That's equal to our total weight, which again splits into two pieces. I have the mass of the equipment plus the mass of the hot air, which is going to be the density of the hot air times the volume of the balloon, all multiplied by G. So this is basically what we did before, except we're adding in this little helper term that's helping the buoyant force just a little bit. The G's cancel out again. And again, we're going to subtract the V containing term from the right-hand side and factor it out. That gives me a V times rho cold minus rho hot. And then on the right-hand side, what I'm doing simultaneously here, I have MEQ over there, but I wanted to subtract this new term, rho cold times VEQ. So I have minus rho cold VEQ. Now we can solve for V, and I get MEQ minus rho cold VEQ, volume of the equipment, divided by the difference in the two densities again, rho cold minus rho hot. So now we can plug in our numbers, and the mass of the equipment was 500 kilograms, the density of the cold air 1.24 kilograms per cubic meter, the volume of the equipment and passengers 0.333 cubic meters, and we're dividing by 1.24 minus 0.95 for the difference in densities. And when I run the numbers on this, I end up with 1,723 cubic meters. In other words, improving our approach to the problem to include the buoyant force on the passengers and equipment themselves made a difference of 1 single cubic meter in how much we need to inflate this balloon. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.